Hello, math learners! Complex roots of a polynomial. Recall that complex numbers are all numbers of the form a plus bi, where a and b are any real numbers, and I is the imaginary number that is the square root of -1. Simplify the following. Square root of -25. Well, you can break apart the -1 and the 25 and square root them separately. Square root -1 gives you the imaginary number I, and square root of 25 is 5. Normally this is written though as 5i. Square root of -50, you want to break off the -1 and factor the 50 so that there's a perfect square involved if possible. You wouldn't want to factor it as 5 and 10 because neither 5 and 10 are perfect squares, but 25 and 2 work nicely. Root 25 is just 5, the root -1 is I, so you would say that this one's equal to 5i root 2. We don't like to put the root 2 first because it can be confusing if the radical is including all of it or not. That's confusing, so just put the radical last. When you're combining two complex numbers, 4 plus I minus 1 minus 3i, just remember to distribute the subtraction. So we get 4 plus I and then minus 1 plus 3i. So now we just do 4 minus 1, combine the real parts, and we get 3, and then combine the imaginary parts. I plus 3i is 4i. So there's our simplification. Let's go ahead and circle some of these answers here. When you multiply two complex numbers, you must FOIL. Notice that these complex numbers are identical except the imaginary part is opposite sign. Just so you know, when you have a plus bi, then a minus bi, these are called complex conjugates. Everything's the same except that the sign of the imaginary part is opposite. Now, something interesting is going to happen when you FOIL conjugates. Anytime you have to multiply two complex numbers, you want to go through the FOIL process. 3 times 3 and then 3 times 2i, and that gives me 9. 3 times 2i is 6i. And then I do the other two products of the FOIL. And we get minus 6i minus 4i squared. Don't forget to square the I too. Notice in this particular case, the two middle terms cancel each other. 6i minus 6i, 0 out. So we just get the 9, and we have minus 4i squared. Minus 4i squared, though, is the same as -1. If I is equal to the square root of -1, then square both sides. You have I squared is equal to -1. And so this winds up being 9 plus 4, and we get 13 out of this. It turns out every time you multiply two complex conjugate numbers together, you always get a positive real number back. No i's are remaining, because the o and I from FOIL will cancel, and this I squared will go back to a real number, back to -1. Also, by way of review, we're going to solve this equation. 2x squared is equal to 2x minus 5. This is quadratic, so I'm going to subtract terms from the right to the left and create a 0, and then try to factor this. And if it can't factor, then you want to use the quadratic formula. So let's go ahead and just do the quadratic formula. And we get x equals -b, which is 2, plus or minus the square root of b squared. So -2 squared is 4. Don't forget to square the negative as well. Minus 4ac. 4 times a times c. 4 times 2 times 5. 2 times 5 is 10 times 4 is 40. All over 2 times a. All over 4. Now 4 minus 40 is -36. So as soon as you get a negative inside the radical here, we know that this equation has no real solutions. The two solutions are going to be imaginary because we're going to do a square root of a negative. In fact, this winds up being -36, and the square root of -36 is 6i. So we get x equals 2 plus or minus 6i all over 4. Now you can split the 4 up and say 2 over 4, which is a half, plus or minus, and 6 over 4 is 3 halves times I. And so we get two different imaginary numbers. Now, just so you know, when I say the word complex, that doesn't necessarily mean imaginary. Complex just means it has the general form a plus bi, where a and b are real numbers. So it's possible that a is 0, and so you get just bi only. This would still be considered a complex number. It's called a purely imaginary number if the a is 0. It's also possible for the b to be 0, which means this part is not there. So you still have a complex number, but it's just a real number. So we either have real or purely imaginary, or a combination of the two. Those are all the different kinds of complex numbers you're going to have. So all real numbers are technically also complex. This number here, 13, is complex. So is 3 plus 4i. So are these numbers. Those are complex. If I say imaginary, though, then that means I is involved. And if I say real, I say I is not involved. By way of review, next slide. Factor the following quadratic polynomials. First thing I notice is that a 2 can be factored out of both of these terms. So 2 times x squared minus 9. And then you see a difference of squares. A squared minus b squared factors to a minus b times a plus b. So applying that to this, we have 2 times, this would be x minus 3 times x plus 3, and we say it's factored. Let's move on to this one on the top right. Here's a trinomial, and we want to try to factor it into two first-degree binomials. So we're going to split 2x squared up. Well, the 2 is prime, so it's got to go one place but not the other, and the x squared we split. And now we're just going to do the guess and check. we know that the numbers that go here and here have to multiply to be -3. So there's really not that many options. If I put +1 and -3 like this, that turns out it works out when you FOIL. Let's say I didn't do that though. Let's say I did this first, and when you go through the FOIL process, where we have 2x squared plus 6x minus x, that's plus 5x, and then -3, but it's not giving me this term here correct. So we need to rearrange, maybe move where the plus and minus are too. There's lots of different things you might need to do to make this right, but it seems like if I put -3 there and +1 there, that we get a factoring. Go ahead and FOIL it and you will see that it works out. All right, this next one, again, I see a 2 can be factored out, and that leaves us with a sum of squares. And sum of squares does not factor using real numbers. You might think it's maybe doing this, but when you FOIL this, there's going to be a 6x, and there's no 6x. So that doesn't work. And anything you try with only real numbers won't work. So we say that this is prime. That's prime as far as the real numbers are concerned. But if you allow for imaginary numbers, it factors like a difference of squares would. In fact, we can say a squared plus b squared is not prime if you allow for imaginary numbers. It factors to a minus b times a plus b, which is exactly how the difference of squares factors, except that there should be i's attached to these b's. So it really factors to a minus bi times a plus bi. Now I'm going to leave it to you to verify this, that when you FOIL this, you do get a squared plus b squared, because the I terms will either cancel or the I squares will become -1s, similar to what happened here. Okay, so with this in play, we can factor x squared plus 9. It factors to x plus 3i and x minus 3i. This part here does not factor over the real numbers, but it does factor over the complex numbers. That just means if you allow for I as well, then you can factor it. This 2x squared minus 2x plus 5, that looks familiar. That was the exact same thing right there. If you try to factor this one in the classic sense like this, you won't get anywhere. Instead, what you want to do for a problem like this is do what we've already done, which is the quadratic formula, get the two answers, and then if you do x minus each answer, that will be how this thing factors. Okay, so what I mean is the two answers, let's copy and paste these down here. There's two of them actually. I'm going to split them up. One will be plus, one will be minus. And then we can factor this quadratic by doing x minus each of these roots with the leading coefficient factored out to the front. So what that looks like, leading coefficient factored out to the front, and then you do x minus, and then this goes in right into that spot. And don't forget to put this in its own parentheses. And then the other one will be similar. Again, x minus, this one goes in right here. It should be in parentheses. And then we can close the overall set. And this is how you factor a quadratic that has a leading coefficient other than 1. So this had a leading coefficient of 2. And so we factor it so the leading coefficient's in front. And then we have x minus one of the answers, x minus the other answer. Now this is exactly what would have happened if we had done this one the same way. Let's just verify that real fast. Let me do the quadratic formula. Let's pretend this was set equal to 0 and that we solve for x. And the quadratic formula would give x equals negative b, so 1 plus or minus the square root of b squared, which is 1, minus 4ac. 4 times 2 times 3 is 24, but it's negative, so it's going to go back to positive 24, all over 2a, all over 4. So we're going to get a couple answers. X equals 1. That's going to be a radical 25. That's 5. So plus or minus 5, and then all over 4. So we get 1 plus 5, which is 6 over 4, which is 3 halves. And with the other one we get is 1 minus 5, which is negative 4 over 4, which is negative 1. So we would take these two answers, pretend like we didn't know this. We would factor the leading coefficient to the front, and I would do x minus and then each of these two answers. So we'll do x minus 3 halves is one of our factors, and the other one is x plus 1. So here's another factoring. Well, how are these the same? Is this the same as this? The answer is yes. If you take this 2 and you distribute it through this first set of parentheses, you don't need to distribute it to both, mind you, because there's multiplication right in between these. Right? In the same sense that if I say what's 2 times 3 times 5, you would only do 2 times 3, get 6, and then times 5 and get 30. You would not do 2 times 3 and 2 times 5. That's too much. But if you have 2 times 3 plus 5, then you distribute. As far as this 2, it does not distribute to all 4 of these. It just distributes to one of them. You pick. So we're going to distribute through this one here, and that gives us this term here. So yes, we have a factoring. This process of using quadratic formula and getting your answer that way, and then putting the leading coefficient in the front, and then doing x minus each answer that you see here. And that's all we simply do for this one here with the imaginary roots. So we have a 2 in the front. I'm going to go ahead and get rid of the orange parentheses. So we have minus a half minus 3 halves I. And then the second one is x minus a half plus 3 halves I. And I leave it to you to verify that when you FOIL this, that all the i's will cancel. Then you're going to double everything, and it should wind up in the end just being this expression. The Fundamental Theorem of Algebra states that a polynomial of degree n has n complex roots. but not necessarily distinct. I'm using the word complex as well to imply that imaginary numbers are on the table. They are allowed. So a third degree polynomial will have 3 roots. A and B not all different. So it could be the roots are 5, 7, and 7. The 7 got repeated. Or it could be 5, I, and negative I. In other words, I is allowed. Or a fourth degree might have 7, 7, 2 plus I, and 2 minus I. The next line here states that the non-real roots of a polynomial with real coefficients, so when you're in expanded or general form, there's no i's. If you have such a polynomial, and that polynomial has a non-real root, then it'll come in a complex conjugate pair. In other words, if a plus bi is a root, then so is a minus bi. Right, we saw that happen in a problem like this. When we tried to find the solutions to this, we got 2 non-real roots, and one was a plus bi, the other was a minus bi. So we're going to combine these 2 theorems and allow us to do the following task right here. Find a third degree polynomial. That tells me right away there has to be 3 roots with real coefficients. So that tells me that the roots have to come in complex conjugate pairs if they are non-real. And we want this polynomial to contain the point -1, 3, and 2 of the roots are given. Okay, here we go. I'm going to make a little table. I'm going to list the roots in the table and then list the corresponding factor. 2 of my roots are 2 and 1 plus I. I need a third root if I'm going to create a third degree polynomial. And the third root has to be the complex conjugate of this non-real root. So we have to have 1 minus I as a third root. If a root had been 3i, then negative 3i would have been another root. You just change the sign of the imaginary part. Don't change the sign of the real part. The 1 stays 1. Okay, next part, to create the factors. It's always x minus the root, x minus the root, x minus the root. So these numbers here are just going to be moved right there. And use parentheses on the non-real ones here. Parentheses 1 plus I, parentheses 1 minus I. So to create our polynomial next, be a third degree. It's going to have an unknown coefficient, and we'll just call that a for now. And the 3 factors get multiplied. X minus 2, and then I'm going to distribute the negative across there. So we have x minus 1 minus I, and the other one's going to be x minus 1 plus I. Now we want to expand all this, put it in general form. I'm going to begin by expanding these parts. It'll be a lot easier to expand the 2 complex conjugate factors. And to expand, we're going to have to distribute first the x across. So that's going to give us, I'm going to leave these first 2 parts untouched. So distributing the x, we get x squared minus x plus ix. Now we distribute the -1, and that gives me negative x plus 1 minus I. And then finally we distribute the negative I, and that gives us negative ix plus I minus I squared. Okay, now let's look for things that are similar, like this negative x and negative x, they can combine. The ix and the negative ix are going to cancel. The negative I and the positive I are also going to cancel. And furthermore, this I squared, that's going to be a -1, so that I is going to turn back into a real number. So let's see what we wind up getting next. P of x equals unknown coefficient, leading coefficient, times x minus 2 times, we had x squared to begin. The 2 minus x's become minus 2x. Everything else that's double or triple underlined canceled. We still have that plus 1 that's not underlined right there. And then over here is going to be a minus -1, so another plus 1. So plus 1 plus 1. So that gives me a times x minus 2 times x squared minus 2x plus 2. Now we're going to do this foiling right here. So I'm going to distribute the x across there and then the -2 across there. Distribute the x first, we get x cubed minus 2x squared plus 2x. Now distribute the -2, minus 2x squared plus 4x minus 4. Look for any similar terms, I'll underline them. -2x squared are similar, and 2x and 4x are similar, nothing else. So we get p of x is equal to some unknown leading coefficient times x cubed minus 4x squared plus 6x minus 4. So here's our polynomial. Changing a is just going to do different vertical stretches of it, but we want to do the vertical stretch and or reflection that'll guarantee we go through this point here next. So we're going to change the output to +3. At the same time, we change the input to -1. So all the x's are going to become -1s. So I have a -1 cubed minus a 4 times -1 squared plus a 6 times -1 minus a 4. So now let's simplify this. 3 is the output. We have an a times -1 cubed is -1. -1 squared is +1, so we just get -4 there again. And we get -6, and then minus another 4. And all these negatives are going to combine to be -15, and then we divide both sides by -15, so we get a is equal to 3 over -15, which is just the same thing as -1/5. And this now is going to allow me to write my final answer. Polynomial we're looking for is -1/5 times, and then I'm just going to copy paste this. If you want, you can distribute the negative 1/5 across the parentheses as well, but we'll call this good enough. And now let's go to the last slide. And the last one, find all the complex roots of the polynomial below, express the polynomial in factored form, and graph it without technology. All right, so scan this and make sure that every coefficient is an integer, and it is, so we can use the rational root theorem we talked about in the last lecture. Let's do our list of p's over q's. And the numerator is going to go all the factors of the, oh look, there is no constant. Constant 0. This tells me that we should do a step of factoring immediately. We can at least take an x out of all this. And if you want, you can factor the negative out with it. So let's begin with that factoring. So I'm going to rewrite this thing down. Negative x to the 5th minus 3x to the 4th minus 2x cubed plus 2x squared plus 4x. I'm going to begin by factoring out the negative and an x. So we get negative x factored to the front. That leaves x to the 4th plus 3x cubed plus 2x squared minus 2x and then minus 4. This polynomial is going to become the one we want to focus on. We'll do the p's and q's for that. So the constant is 4, and all the factors of 4 are 1, 2, and 4. The leading coefficient is right in front of that x to the 4th. It's a 1, so all over a 1, which just means we just get plus or minus 1, 2, and 4. Now we want to set up our synthetic division. Again, we're really just trying to factor this quotient here that's in the parentheses. So I'm going to write down our test number is going to go in that corner, but then the coefficients of what I just underlined, which is 1, 3, 2, -2, and -4. Again, I'm going to leave some space right here so I can do a factor tree at the same time. And we're going to start cycling through these numbers and test them out. Let's start with the plus minus 1. Put a 1 there and see if it works. Bring 1 down, multiply, add, multiply, add, multiply, add, multiply, and sure enough, look at that. We get a remainder of 0 right away. This tells me how this factors. Well, the negative x just stays, but this quotient factors to x minus this number right there, so x minus 1, and then the other factor is this quotient, which is going to be a cubic. X cubed plus 4x squared plus 6x plus 4. And now our focus is to continue to break down this quotient. So we just get to use these numbers here and do more synthetic division, looking for a remainder of 0 right here again. Try the 1 again though. Always keep trying the same number as long as it keeps working. 1 drops, 1 times 1 is 1, add 5, multiply, add. This is not going to work. I can see right away. So we can now cross 1 off our list. Let's shift to -1, see if that does anything. Bring the 1 down, multiply, add, multiply, add, multiply. Doesn't give me a 0 here. So -1 is off the list. Let's keep marching down. Let's go to 2. 2 is not going to work. I can see that because all the numbers are positive. We're just going to compound issues. Nothing's going to cancel. So let's try -2. Bring the 1 down, multiply, add, multiply, add, multiply, and sure enough, we get that 0 there. So I found some more factoring. So the negative x is still there. This x minus 1 is still there. But I just factored this quotient into x minus this number, which is x minus -2, or x plus 2. And the other factor is this quadratic, x squared plus 2x plus 2. Now you really want to keep this up until you get to a quadratic, and then you can use the quadratic formula or just try to factor it in the traditional way. Well, this will not factor in the traditional way. So we're going to have to use the quadratic formula on this. Let's do that work over here. We're effectively solving this equation, and we're going to get x equals -b plus or minus the square root of b squared minus 4ac, that's going to be minus 8 all over 2a, which gives me -2 plus or minus, that's going to be -4 inside the radical, so a 2i all over 2, so the 2 can split and simplify each, so we get -1 plus or minus i. These are the last two roots, which means the last two factors are, let's go ahead and bring these factors all down. So one of them is going to be x minus one of these, so x minus -1 plus I will say, so that ends up being x plus 1 minus I, and then the other one's going to be x minus -1 minus I, which distribute, we get x plus 1 plus I. And there's our final two factors. So this has the general form where we have the leading coefficient in the front, -1, and then times a bunch of linear factors that reveal all the roots. Now, mind you, when you're graphing, it's only the real roots that are going to be x-intercepts. So when you look at the roots themselves, you set each factor to 0. You could see this is a little x minus 0 there, but x by itself as a factor means that 0 is a root. Set x minus 1 equal to 0 and solve, you get 1. You get -2. And this one is the one that gave us -1 plus I as a root, and this is the factor that gave us -1 minus I as a root. And you can see we have 5 roots. All of them have an odd multiplicity. This was a 5th degree polynomial, so we only had 5 roots to look for. Some of them did involve I, and some were real. The real ones are the ones that are x-intercepts. So 0 is an x-intercept, 1 is an x-intercept, and negative 2 is an x-intercept. Furthermore, we know that the graph will cross the x-axis at each of these locations because the multiplicities of these x-intercepts are all 1. The imaginary roots, the non-real roots, don't affect the x-intercepts. There might be some extra like wavy wonkiness going on in the graph, but there won't be any more x-intercepts that we can see. So how do I get the rest of this graph going? Well, one way is to look at the leading term. This is negative x to the fifth. And a negative leading coefficient with an odd degree means we're going to start high but finish low. So that's really enough to get us going here. And I know I have to cross at each location. It's going to have to be something like this, maybe with some extra bumps here and there, but this is going to be the basic shape of your graph. I leave it to you to graph this on Desmos and see how it compares to what we found by hand. And that wraps up our lesson on complex roots of a polynomial.